Hello, everybody. Welcome to your weekly webinar number 9 with me, Michael Floyd. I am your mentor and your mentee. You learn as much from me as I hope to learn from you. Now, back to these same things. The introductory forms, still only 5 out of 14 of you still have not emailed me or filled out on Calendly to fill those out. Get back to me if you can. Setting the pace for this course as well. 8 out of 14 have incompleted it. One of them has actually submitted it, so I'm hoping it becomes 7 out of 14 by next week. Still, we are more than halfway done, and not even half of the people have completed the first project. I'm hoping we can make this work. I don't want everybody to waste their money. I know this can be difficult. Let me know if you have any problems. Like I said, 30 minutes in the morning, 30 minutes at night. Now we might need maybe 45 minutes in the morning, 45 minutes at night. But I'm hoping with that we can get this done. And, to let everybody else know that you are spending time doing this, just write on Slack when you completed a project or when you completed a lesson or anything of that nature. Okay? And like I say in every one of these webinars, we have a case of how time was spent for 3 students. We have student A, student B, and student C, right? Student A does not have any responsibilities. It should be easy or a picnic for him. Student B and C, on the other hand, have jobs and children. But student C stays consistent with his schedule while student B inconveniences everybody else around him. Let's try to be more like student B and inconvenience everybody else around you in order to get the job done. All right, so this webinar is on clustering methods. That is going to be part of your next project. I know we're all still working on the second project, but in order, they wanted me to do this on this time. So I will begin showing you the clustering methods and things about it. As opposed to just using the Udacity lessons, what I decided to do was use the different articles that I found on the internet. So you can use these articles as well as the lessons that Udacity provide, which are very, very direct and understanding of everything that goes on. So without further ado, I will share my screen. All right, I'm sharing my screen. Okay, this is the first article that I wanted to show you. It's on Medium. It's just 5 cluster algorithms that data scientists need to know. That's what they say data scientists need to know. And they give pretty great examples and also show you how these algorithms converge as well. The first algorithm is the k-means clustering algorithm. Now, the k-means is called k-means because you choose how many clusters you want. So the k is the amount of clusters you choose, and as you can tell, this is actually an example of how it works. So what k-means does, well, also, so as you can see, it moves the x's, which are the means or medians, depending on what you were looking for as far as your data set. The x's move according to how the means are in the data. You can see they move towards the center of the 3 clusters. And this is just a couple of writings on exactly how it works. So we first select a number of classes or k clusters, and then we choose x to randomly place exactly where the clusters start, and then we find the mean of those center of the clusters. We then look and see exactly what points or around or closest to that mean and basically points that are closest, we assign it to that cluster, then recompute the mean. So like it says right here, each data point will be classified by the distance to the center of the mean. And then you recompute the mean and keep on going until nothing changes or doesn't change much as far as the mean of the clusters. And the thing about the k-means is that k-means can either not converge or it can converge. So sometimes the problem you may have or may not have with k-means is that it can depend on where you start these points as far as randomness. So what sklearn does, I believe, all by itself, is sklearn actually starts this many different times. So you have random points started many different times. Then sees which one is more prevalent as far as the one that is converged, the place where it converges the most. So it is possible to sometimes not get the same effect, depending on exactly where you place the points as far as convergence. Another thing about k-means is that when you are deciding on k, or how many classifications or how many things, how many clusters you want, right? That will also depend on your data and what you're looking at. So what you actually do with k-means is, I believe this is it's okay. So what's going to happen is you want to look at your different k's or your different number of centers that are the different number of clusters that you want. So when you look at k, you will keep counting the number, well, you will keep increasing number of k's until you get a graph similar to this. And what this is you would have the distance to the centroids, and you will have the number of k right here. So as the number of k increases, of course, your distance to the centroid will decrease. So, of course, if you have only one cluster, then the distance to the center of that one cluster will just be all the data points, the average, the distance from the mean of all the data points. Whereas if you have only 100 data points and you have 100 clusters, your distance to your centroid is 0. So this, what you will have is a graph that generally converges, such as this. And what you are looking for is you are looking for an elbow point, or a point, similar to this nature, where, as far as the extreme convergence, it then decreases very, very slowly. So you're looking for this elbow point right here when you are looking for how to pick the number of clusters. So that's how you choose your K. And, there are good and bad things about the k-means. One advantage is that, you're looking for is convergence as far as where your points are. So you do have an ON complexity. And it also talks about the disadvantages here, right? The selecting the groups of classes is probably the biggest disadvantage, because you do have to find that elbow, have a good insight on exactly how many clusters you would want to produce or should produce given your data set. Okay. And, like I said before previously, you don't have to always use the mean. The median is sometimes most of the time, a way more robust tool to use. And, if there is another distance metric or a different metric that you like to use, you can also use that as well. This paper does talk about many different distance metrics. Okay, I'm not looking for a place where it talks about the many distance metrics. Yeah, I just found it. Okay. So you see, Euclidean, cosine, Jacquard, edit distance. I mean, whatever you choose as far as a distance metric, it is, it should be based on what you are doing and what you need as far as your data set and what you're trying to reveal. Okay. So mean shift clustering. So what mean shift clustering, like it says right here, a sliding window. So a better observation is this right here. It's on 10. I'm waiting for it to restart. As you can see, the number of you're looking at these black dots. So you start off with all of these points, and what you do with all of these points is you find the begin with a circular sliding window, and the window has a radius of r, and then the points are shifted towards a region of higher density, like it says right here. So, when the points keep shifting towards this region of higher density, they all will basically converge into one area, like you see right here. And, these points right here will converge into this one area. These points right here will converge to this one area. These points right here will converge into this one area. And so what you have after that iteration, you then have a 4 clusters, and then you can see exactly which belongs to which by just looking at the distance and how far as distance. And if you have a small dimension, you can also just see exactly how it looks as far as graphing as well. So that is what happens with mean clustering. As you can see, this is just showing right here, the point is moving to the place of higher density based on the points within its radius. So that's what they are all doing right here. That's just showing you what they're doing. And the third algorithm is the density-based spatial clustering of applications with noise, or DB scan, which I call it. And sounds really complicated, but this algorithm is not that complicated. So what you start off is, you start off at any point, right? So you do this for any and every point. So what you are looking for when you start off at a point is you are drawing an epsilon or a radius around that point. And then based on the number of other points within that radius, you then conclude whether that it is a cluster or not a cluster. So for example, if I was to choose this point right here and look at an epsilon radius of, let's say, 100, there are no points within this epsilon radius of 100. So therefore, it is not a part of a cluster, and it is not a cluster. However, looking at this point, an epsilon radius of 100, there's more than 4 points within this radius. So now it's a cluster. And then you move on to a point right next to it, and this is a cluster. And because they are a part of the same radius, then they are part of the same cluster. And that's what keeps going on over here, as you can see. So, I mean, this is doing it for multiple points at a time, but this is pretty much how it is working. So it keeps going. You looks at all of these points, including these points over here, which are not classified as a cluster. So that's one thing that DB scan does that's different from all the other ones. As you can tell, is you end up having 4 clusters. One, the circle, and the cluster right here, the cluster right here, and the cluster right here. But as you can notice, when it's complete, I can pause it and actually just notice that, which is great. I'm actually going to pause it in a second. Crap. Okay, did not pause. It says it can pause. I'm not okay, but if you can pause, it would show that once it has completed all of these, and then you have the 4 clusters, 1, 2, 3, 4. It ends at just those 4 clusters, and these points are not classified. So all of the points that are not within the cluster are not classified. They are actually referred to as outliers in this case, which is actually something that's a lot different as far as DB scan that is not in the other algorithms. That you do have outliers based on the distance away from your points, and it's one big thing is the outliers as far as DB scan. And of course, you can change the epsilon, which is the radius around the points. You can change the number of points that are necessary in order to be a cluster as well. So all of that will definitely influence. And I believe this is actually, is this how you change the epsilon and minimum points? It's not. Maybe it was, but it's not. It'd be cool if it worked. Okay, yeah, and this is, it tells you exactly how the DB scan works with the epsilon and the minimum number of points, and yeah, the process keeps repeating until all the points are determined, and that's pretty much yeah. Okay, that's yeah. So then here it has some advantages and disadvantages of it. You know, and it's the main drawback. The clusters are varying density, and you also have to set the epsilon and the minimum points. So that can also be relatively tricky, especially if you have multiple dimensions. And one thing also about the clustering, whenever you are clustering things that are numerical in nature and not necessarily ordinal or nominal, what you want to do is you want to make sure that you normalize or standardize the data. So that is also important, right? So the distance is important because the distance between the points is what you're looking for. So make sure you normalize or standardize the data based on the type of data that you have and your preference and what makes sense for the time. And the expectation maximization clustering using the Gaussian mixture model. So what this does is, so here's a great example of this as well. You start off, okay, we set it to 2, which is similar to the k-means. Is you set the number of Gaussians that you would like to be fit. You start off with 2, and what you see here is that Gaussian is a normal distribution. So you start off with 2 random points, which are the centroids of your cluster, and using the expectation maximization, or how likely it is that this point is in this cluster or the other cluster. So in this case, we only have two clusters, so it's either in one or the other. So based on the distance from that cluster and the standard deviation, there is a probability that it is a part of that cluster, because we're looking at normal distribution. So based on, if you know that probability and you know the probability of the other cluster, you can then normalize. We'll take the sum of these two probabilities and divide the one probability, and you will find the probability of being in one cluster or the other. And for multiple clusters, you'll have multiple probabilities. So just find those different probabilities, and then whichever one is the highest, of course, that will be the maximizing of the expectations. So the expectation maximization, and then you set that to be in that cluster. And once you know which data points are in which clusters, then you will recompute the mean and standard deviation, and do it again. Figure out exactly which points are in which cluster, and keep doing this until you find some sort of convergence, which is like the k-means as far as you pick the number of clusters. But the cool thing about the Gaussian is that what you see here, obviously, is that uh, all the other uh, clustering mechanisms will perform with the expectation that what you will be observing is a circular circular uh, a circular deviation from the mean. That is what's expected. But as you know obviously know, most of the time you do not have a cluster, and perhaps looking at this, you can tell both of these are not circular in nature whatsoever, right? So what a k means, what the mean shift would have done is would have looked at this and looked and said, in a circular fashion around the mean, what is the uh, placement of the points in the cluster. And this more, because you're, looking at a normal distribution and, in multiple dimensions, you don't have to just have the same circular fashion. You would actually, be able to have different variances in the different dimensions. So that's what this talks about. Um, and about here, you have a deviation that you can also sets itself. So and this is just how the Gaussian what is this called? It's called the Gaussian mixture model is done. So like I said, based on probabilities, you can use a set of parameters. It's just repeating exactly what I said, maybe in a different fashion. So, re-looking at this, and also the notes from Udacity do give a great visualizations as far as detail and everything as well. I chose to not use the notes from Udacity. I chose to try to show you different things. Like there are plenty of websites out there now, especially for machine learning, that are definitely showing you the advantages and disadvantages of different clustering techniques. And okay, and so like I said before, this shows you the advantages. The covariance that I was mentioning before, because the standard deviation for the different features can be different, right? So like I said, they can take on a lip shape rather than be restricted. Pretty much the exact same thing with what I said. So like I said, I try to and agglomerative hierarchical clustering, I believe, is the last one of this article. So what you have is you have the hierarchical clustering algorithms that well, okay, I'm gonna try to read that. So pretty much what you do with these hierarchical clustering is you start off, everything is not in a cluster, and then you choose which ones are closest to which ones one at a time, and you eventually get something in a hierarchy similar to this, right? So that is hierarchical as far as going from the bottom, having nothing in a cluster, and then going up. And there are also clustering algorithms that start off with everything in a cluster, and then removes the ones that are dissimilar by nature, and you would then going uh, from a I guess that would be a top down approach, right? Well, yeah, that would be a top down will have all of them in a cluster, and then removing the ones that are dissimilar, and bottom up is the ones that are nothing is in a cluster, and then based on the distance that are between two clusters. In this case, we have 0 connected with 1 and 2, or 2 points. In the case, we have 1 and 2 connected, and 5 and 6 connected. you will find that intercluster distance and see which ones are similar. The closest. And if that is the conclusion, sklearn also has all of these. sklearn is great because sklearn has all of these algorithms there for you to tinker with, and plus they have many different parameters belonging with the algorithms that will also help you as far as definitely finding the best fit and the best clustering algorithm to use. And this is actually an example of different clusters and different spaces you have and how each different algorithm worked. This article did go into spectral clustering, but it went into mean shift. It went into, this is k-means, and it went into agglomerative clustering. It went into dB scan, and it went into Gaussian mixture. So this is just showing you exactly how it performed, given it went into all of these, the algorithms that it performed. You see for the k-means, instead of finding the two rings, that was the point of this, k-means, it's the two means that you're looking for. So close, it will split and go and have one mean at this point and one mean at the other point. And what's cool is this is actually a great example. And if you would start, let's say, 1 point down here, 1 point up here, most likely your means will split somewhere in this direction. So when you have these splits, in this case, in the vertical, you might have a split in the horizontal, and all that will do is signify that the placement is different as far as where the cluster started off with. And because the placement was different, the algorithm did not perform similar. But in this case, it's not important. This k-means is not a great use for this one anyway. And here's an example where you do have two clusters. And you see how k-means does similar in this fashion. You have part of this, but not all of it. And you also take part of this because you're looking for a mean around a centroid part. So that is the problem with k-means. And here you have three clusters as well, right? So, we know there's three clusters, so we'll just assume that k was chosen with three. And as you can see with three, you have three medians, but not everything within this cluster is actually part of that cluster. And some of the green is chosen up here as well, and some of the blue. So one thing you should know about dB scan is dB scan, not all of these points as far as dB scan need to be a part of not all these points in dB scan need to be a part of a cluster, which is pretty cool. I'm not sure what they use as far as epsilon and minimum number of points in this case, but the cool thing about dB scan is you can see we have outliers in this example, and those outliers should not be part of points. They just be inside clusters like this dB scan should produce if you choose the right parameters in this case. I'm not sure what parameters they chose. And this one as well. You have three clusters, but you can see the k-means does not do well as far as detecting the difference between these three clusters. And remember, these look very, very similar to how you would expect a Gaussian mixture to perform, right? And you would have three clusters right here. K-means does very well on this, but as you can tell right here, all you have is a whole bunch of data points. And with this whole bunch of data points, you choose three clusters, and you will get three clusters. And the problem with this is that they are clearly only all these data points are evenly spaced. It's not seen to be a placement as far as the number of clusters. So this looks like just one big cluster, big mess of just points in a plane. But because you set it to three, the k-means will be a three. And that's something that the mean shift does well, is that it puts different points in different placements around, and then based on exactly the centroids, it would then compute and it would then find the center and then converge all those points to that center point. And the so like we said before, the agglomerative clustering does well for this one and for this one, right? Finds points that are similar, and then based on the points that are similar, you would then compute the number of clusters. So agglomerative clustering in this case would have most likely had two different hierarchies that are pretty spaced apart. And then once those hierarchies are found, then what it could do is you can see, which, the spacement of these points of the hierarchies, they just cut it right here because you see there's obviously two clusters similar to what you do here. Now that all the points are connected, you can see that we have really looks like three clusters here, right? So we have a set of points that are very closely related, another set of points that are very closely related, and we have this, it looks like an outlier. So here we can cut it right here and see that there's three different clusters, this one an outlier with no clusters to itself. And that's something similar to what an agglomerative would do in this case, where obviously two very similar placements or clusters. And then we can just cut it exactly, and once everything is put together, and then say that, hey, there's two clusters, that these are the points that are within each cluster. Okay. And so agglomerative does well for this. The DB scan should do well at this point. In this case, the Gaussian mixture should do well. They all seem to do well when there's just three blotches of clusters, which is that's the easiest case, right? Just three distinct clusters. They all perform very well. It's three distinct clusters that are circular in fashion and no outliers, it would seem. So everything performs well in this highly unlikely case that you see, that you will most likely never see in any data set. And the DB scan also does well on this as well. And the agglomerative, as you can tell, you choose the number of clusters. So the agglomerative, you have points at the bottom right here that might be a little dissimilar, that it says that, oh, this might be another smaller cluster. But as you can tell, this most likely, if you were looking at what you were looking at as far as agglomerative, you could choose where to start and stop this. And the DB scan, which is a density-based scanner, it also picks up, there's only one cluster, which just goes around, and based on the epsilon, the number of points within, chooses this. So this is an example of when and where these algorithms will work. All right, and the sklearn has documentation for the ones here that are not stated. The affinity propagation, the spectral clustering, the Ward, and the Birch, all are different things in sklearn that will share with you how these algorithms work as well. But these should be 5 great clustering algorithms to start off with. And these papers right here that I looked up, one's from Stanford University, and just showing you as well the point of clustering, right? So when you were doing our supervised learning, right, we had a predictor, that's something that we wanted to predict. So that's what's different between supervised and unsupervised, because in our supervised, there's something we needed to target and predict and have a model that actually predicted that on a good target. But something different about unsupervised is that you may be given, for let's say you have a whole bunch of dogs, maybe given their height, their weight, their skin color, their nail size, all these things. And what you're looking for is you're looking to categorize and set those up. As you can tell, height and weight are the best things to categorize. That's if you have a whole bunch of parameters based on just you tuning out parameters and figure out what you want to observe and what you can observe from the data. So if you had a whole bunch of parameters as far as a whole bunch of dogs, you chose the height and weight, and you separate them. You realize that Chihuahuas can be separated and Dachshunds and Beagles can be separated. That is something, right? So what else do we use clusters for? We use clusters for um, a lot of things in biology. You have your plants, your animals, your genotypes, your phenotypes, um, and this is another paper that gives you the analysis for to tell you stuff about concepts and algorithms for cluster analysis, and it talks about what you're using clusters for, understanding or utility, right? So, understanding, like classifying into buildings, vehicles, people, animals, plants. Like I was saying before, and here you have a whole stuff on biology, the information retrieval that you would have as far as internet, uh, climate, the psychology of medicine. This gives you a whole bunch of examples of what you can use as far as clustering and to understand what you're getting at as far as your data, and clustering for utility. And yeah, so let's say about utility. So summarizing. Well, this isn't really clustering actually at all. It's using the components that will be actually on a different, so the nearest neighbor also, right? So if you want to know something about a particular object, you can always look at the objects that are closest to it and then get a general idea of what that object is, isn't, or how is it different from the objects that are most related to it. And uh, with that being said, I will post that on these three. I will post these three PDFs or these three articles. And with that being said, I will open it for any questions if anybody has any questions. I will be looking at Slack message board and posting questions on the Slack message board. I will give it another couple of minutes. That's a post on Slack. I don't see anything on the group chat either. Yeah, post on Slack if you have any questions.
I'm gonna throw those toys that I just bought you in the garbage if you act like that. No, thank you.
All right, so there's not any questions. What I'd like you to do next week is let's focus, well, this week, let's focus on completing the second project and let's get to it, okay? If there are any questions, feel free to reach out to me. I actually want everybody to schedule a Calendly meeting with me either tomorrow or Wednesday, and I will be posting that on the message board as well. All right, this is the Nine. Thanks for watching this. Peace.